computer. Good. Okay. We are running a little bit late. That's my fault. I missed 3 lectures lately. The first one was an issue with a case of plagiarism. When plagiarism is when, in this case, is colleagues who claim their papers, my papers and others, as their own, and that was really bad. And these are colleagues from Cerro Calan. So I learned the news in the morning of the lecture, and I couldn't think about anything else. And I alerted the authorities, and well, there's a legal process going on at the moment. So that, sorry for that, but it was really urgent, and I had to act immediately. And then a week after that was this conference I attended. And it was a conference in Europe, so all the talks were in the morning, so I couldn't attend. I mean, it was simultaneous with the lectures, okay? And Rafael was at the same conference. So I'm sorry to have missed all the last 3 lectures. It was unavoidable, I think. But this week, we should be finishing this first chapter on radiative transfer, so we can at least carry out the first exam next week. That's my plan. The plan is to wrap up this chapter on radiative transfer this week. So as you see, there's not that much to be seen yet. There's not that much remaining, I mean. And so in the little, we'll have a lecture now with until 10 only, so it's going to be a half-hour lecture. And then Thursday, probably say the same. Hopefully, if you'll have any questions, and hopefully Nitya and others can join, so that we can have the exam next week. So this means that you'll have a whole week to do the exam. And I'm thinking perhaps we could have a teaching assistantship with Rafael if he's available during this week, in case you have questions. And the idea is to do the exam on your own, of course. But I mean, there's before the exam. That's another thing I need to ask you guys. Have you done your homework? I mean, the chapter 10, all the problems from chapter 1. The idea was to have those homework done before we start the exam, so that you're ready. Okay. So I don't know. Have you had time to look at them?
Yes, I have time to look at them, not as much as to make them.
Yeah.
I do have some question about some of the exercises. So I was going to ask Rafael for help.
Yes. Okay. So it's good you say so, because I want to start the exam once you've finished the homework. So once everyone has handed in their homework, we can start the exam. So please gear up on the homework this week. Hopefully hand them in well, as soon as possible, so that we can start the exam. Pratyush, what's your situation? Have you started doing it?
I think only the first question I have started.
Okay, that's fine, but I think it's time to gear up. Okay, so why don't we, in this case, why don't we aim to hand in the homework by next Tuesday? Okay, so this way we start the exam from Tuesday to Tuesday next week. Is that all right?
Yes, I think that's enough time, a week. So it's every problem at the end of the chapter 1, right?
Yes.
Yeah. Okay.
Okay. And it's okay to ask questions to discuss the problems between you guys. I mean, you can work together, or you can ask for help. All I require is that you learn how to do those problems and that you hand them in to Rafael. Okay. Now the exam is personal work that should not be discussed. Okay. But it's not going to be extremely difficult. It's the exam is going to have references and it's guided, right? So it's not like a super difficult question without any help at all. But the point here is just to have an instance to do personal work for the exam, okay? But the homework, on the other hand, can be discussed. You can ask your fellow classmates or even Rafael. It's okay to ask questions, okay? So try to solve them, and if you cannot, then ask Rafael. And I think the questions, the problems are solved at the end of the book also. Okay. So back to the course. So the uniform slab, the Rosseland approximation. Okay, so last week we went through the Rosseland approximation again. Okay, I know I need to share screen. Of course, you're not seeing anything. Sorry. Share. Okay. Oh yeah. So this is the Rosseland approximation. Sorry, which gives us the flux of radiation. This would be then the flux of radiation in the direction z, given by sorry, given by this definition, right? So this is the vectorial flux, and we project this along z, and we have the flux along z. Flux of radiation in this direction then is related to the gradient of the Planck function. So how does this vary? Of course, this varies as a function of position, because we have this derivative depends on position through the temperature, which is local. Okay. And we went through another. Oh, I remember now. I promised I had to. This is where this is where we left it. And I had difficulties showing equation 50. Okay, so the first equation here is the definition of the radiation moments. So the first one, so this is a set of three equations. Okay, the first one is related to the definition of the mean specific intensity. The second one is the flux we've just seen, and the third is the radiation pressure tensor. This is a matrix. Okay, and I tried to explain this vectorial notation last time. I think it's just to, well, you can look it up on the recording, but basically this is it. This is I can put two indices here. So that would be the integral over solid angles wait. Yes, so we have Ki over K j times I nu k d omega. So for instance, if this is x, y, then that would be sine so that would be yes, sine theta cos phi, that would be ki, times sine theta sine phi for ky times I nu, which depends on theta and phi, times sine theta d phi. Okay, so that's the that's how to read this last equation, which is a little bit cryptic. This P nu radiation pressure tensor. Now, the radiative transfer equation. Then this is the equivalent of remember that the k dot nabla is basically that's not what I wanted to write really. This is what I wanted to write, not with a k but with an s. Okay, so this would be the partial derivative along the direction s. Okay, so now we can read this equation here is like the partial derivative in the direction k, but I don't want to put k in the denominator here because we're using it only as a direction, not as a coordinate in along the direction. Okay, but is this clear to both of you? Is it okay? Yeah. So that's the radiative transfer equation we have with scattering here on the right hand side. Okay. Okay. So we evaluate this the direction integral over all solid angle over this this equation. So last week I explained how we could have that point was that k dot nabla I nu. Okay, so this is the integral over so this is okay, that was the left hand side, and we multiply this by k and integrate over solid angles. Okay, so last time I explained how we could make we could rewrite this term into the divergence of this integral here. So this is in the recording. I don't know if you have any questions on this step. It was actually quite simple in this case because the gradient here acts only on the spatial coordinates. So this gradient here is right. This is derivative on the position, and here and this is a different quantity. This is an integral over the direction, right? So theta and phi. Okay. So I tried to explain last time that we have this situation. We have so this is x, y, z. Okay. And the idea, well, okay, we have once we are given an origin, we have these angles here. So this is we have usual spherical coordinates. Theta and phi then are the directions given this origin, whereas this gradient here acts on the position of the origin. Okay, so that would be the origin here is at some position vector r. Okay, and when we do the gradient, we are varying this. Okay, so what I'm trying to say is that this this gradient is independent of the coordinates of the integral. Is that clear to both of you?
Yes, because that's the, yeah.
Okay. Is it okay, Katyush?
Not really. No.
Okay. So I'll try to explain a bit better then. I'll try to start doing the proof again of this part of the equation. So we have how are we going to do this? Let's split this up in components. So let's write it down. So we have this closed integral of say k j over, this would be like the symbol for the partial derivative along direction j times I nu, okay, times k I. Okay, so that would be the I component of this term here. Okay, Pratyush, as soon as I write something which is not clear, you stop me. Okay. So I want to extract this partial derivative out of the integral. Okay, so first I note that well, these two can commute because well, maybe the best is to write it down in terms of so let's write down an example. So this is actually there is a double sum here. So this is a well, that would be kx dx plus okay, and let's look at the first one. Okay, so the first one, this one here, is sine theta cos phi. So remember to stop me as soon as something is not clear. Times d over dx. That's what I mean by this compact notation here. Okay. So, and this is a partial derivative of whatever. Okay. So what I mean to say is that this is the same as d over dx times sine theta cos phi and whatever. Okay, because the gradient is acting on a coordinate that's independent of the direction of the angular integration. It's because I'm changing the origin, I'm not changing the direction. I can keep theta and phi fixed and move this to another position. This would be R prime, okay, which has got another set of another coordinate Cartesian system, but with the same phi and theta. So what I'm trying to say here is that this gradient is acting on the position and not on the direction. Okay, they are considered independent variables. Is it okay now?
Yeah.
Okay.
Yes, sir.
So if I progress a bit more, then we have that this equation then is the closed integral of so that's going to be dj of kj I nu with a double sum, okay, times ki d omega. Okay. And also this is also independent of the derivative. Okay, so this is like simply a constant relative to this derivative. So I can put it inside the integral, and since the derivative also is independent of the direction, I get it out. So this is going to be dj times the closed integral of kj I nu times ki. And if I write this in vectorial form, then it's going to be the gradient dot the integral of the k vector times ki I nu d omega. And in this version here, this dot product is acting on the first term, and the second one is the one I'm denoting by subscript I here. Okay, so this dot product is acting on the first one, and the second one is just a component. So here are three equations really. Okay, so this is a vectorial equation. Okay, good. So the first term here is 0 because we have the integral over solid angle of a direction k. So let's see why this is 0. We have the closed integral of d omega k. So this is the first term here of the radiative transfer equation, the emission coefficient times j nu. Okay. So this is not dependent on direction. So we are assuming that this thing is independent.
Professor, I think I read in the book that this emission coefficient always depends on the direction.
I think that you're saying, Patrice, that this emission coefficient could eventually depend on direction. Is that what you said?
Yeah, I think what I read in the book previously, I'm telling from the memory. I could be wrong.
No, but I mean it's
I
correct.
think there was a.
It can eventually depend on direction. This could be the case for non-thermal processes such as Mason amplification. Okay, so if you have non-thermal processes, then this this emission coefficient here is not isotropic. Because you have this is called beaming of laser or Mason amplification. Okay, so indeed, the treatment here is applicable only to thermal processes. It's important to bear in mind, but those thermal processes are pretty important in nature still. Okay, no process is strictly thermal, but this is a good approximation many often. Okay. Okay, so this is in.
So we are talking about isotropic case. Yeah.
Yes, it is the isotropic case. Okay, so why would that be 0? So let's look at it in components. So this is the closed integral of, for instance, if I project this. Let me write it down more rigorously. So let's put. Oh. Let's project this along the x-axis. Okay, so that would be of kxj. Okay, and that's going to be then the closed integral of d omega times sine theta cos phi times j. Okay, and since j is isotropic, we get it out of the integral, and that's going to be the closed integral of sine theta d phi times sine theta times cos phi. Okay, so that's j times the integral of cos phi d phi from 0 to pi times the integral of sine theta squared d theta from 0 to pi. Okay. And this one here is 0. So this integral is 0. And so on for the other components. Okay. So now the second term, this specific intensity, when it's weighted in terms of this term integrated over directions, then we have specific intensity. Then when, well, let me write it down. So we have that the integral of the omega k times I nu is what we call the radiation, the vector flux. So this is this equation here, F nu equals the middle equation, okay? So that's the second term, and the one that was giving me problems last time, and I completely forgot to look it up, but let's try it again, is the last term. Okay, so what about the last term? It says we have to do the integral, the last term is then the integral over d omega k times alpha, let's not put the indices, so this is alpha, that's isotropic, times the closed integral of the phase function, which is not isotropic, times d omega prime. Okay. Yeah. So that's let's get this alpha out, and I reordered the order of integration, and let me do an intermediate step. D omega prime times k times phi k prime I nu. Okay, so I'm collecting terms. First, I'll perform the angular integration omega prime, and the only one that depends only on omega prime is this one, I nu of k prime. So this is a vector times the integration over the omega. So what is dependent on omega? So there's this term here and phi times k prime. Good. Okay. So why would this second term be 0? Let's see. This is what I want to develop now. So that's going to be the integral of sine theta. Oh, let's project this. I'll do the same trick. I'll project this into the x direction. Okay. So I'll let me call this. I'll call all this. Sorry. I call this A. Okay. And I'll project, and this is a vector. So it's not a unit vector. It's just a vector. So I'll do x dot A. So the x component of this integral, that's going to be the closed integral of sine theta d phi times ax. And who's the what this is the vector here, so it's going to be kx, which is sine theta cos phi times the phase function, which depends on k and k prime. So instead of putting all these coordinates like this, I'll multiply and say, write it big like this, say this is dependent on theta, phi, and some reference coordinate, theta prime and phi prime, which is the other, okay, so k prime is related to this other solid angle. Okay, so from the point of view of this integral over omega, these prime variables are constant. Okay, so now let's collect terms. So we have the integral of let me see, d theta first. Let's see if it works. Sine theta squared times the integral over d phi times cos phi and I'll put it compactly like this one, okay? So from 0 to 2 pi, and this is from 0 to pi. Okay. What we know is that this phase function should be symmetric. This should be the same as this thing here should be the same as that. So let's look at this. I'm integrating. Let's look at the phi part. So we have I'm going to call this B. So let's call this B is the integral over 0 to 2 pi of times phi and k prime. So this depends on theta, but we don't care because we're only looking at the phi integral here. So this depends on phi and on phi prime. Okay. So let me rewrite this one in terms of I want to do a change of variables. So I want to write phi second equals to phi minus phi prime. So B is going to be the integral over 0 to 2 pi of d phi second. Is this going to work? No, wait. Let me. It's not going to work because cos phi is not. I mean, the change of variable is not going to help me here. I'm forgetting something. Shit. There's a redo.
Professor?
Yes.
In which part of the book is this is this part? And where in the book is this definition, or is it not there?
It's not.
It's not there. Okay.
No. I think I got this from a book by Frank Shu. But the book by Frank Shu says this is obviously zero. Okay. So I know that this is zero. I'm trying to prove it. I did it once and I forgot how. And apparently this to me was obviously zero. And I think there's some symmetry I'm forgetting here. Maybe it's not, maybe I shouldn't go by components. I mean, let's look at what happens. If phi prime is zero, then this is even. If phi prime is zero, well, no, that's not gonna work like that either. This is. Let me try to see if let me try to find which part of the book this is in. Bear with me a second.
Okay. Well, if we are going to use logic to solve this, I would say that is integral, the first step, the one in the when you separate the two integrals, the one that it's going to be zero. I think that looks like a
this one here,
like a weighted average. Yes, that looks like a weighted average of the probability function.
Yes.
So the average of the probability function over all angles, I think should be zero because phi it should be normalized, and that should be proportional to the mean of k, which is in zero because we're integrated over all angles.
Sorry.
No.
Okay, here it is. But
so it's a weighted average of k over all angles.
Yeah, but that's true, Felipe, when the associated distribution function is even, when there is no direction, there's no preferred direction. But here there is a preferred direction, which is k prime. Let me see if I can find this part. I think it's from this book. Just bear with me a second. So this is okay. So I have bad news. This is not discussed anywhere in this book either. Where did I get this from? Oh, no, here you go. Yes, yes, yes. Okay, so I found it. I found it. Let me see if I've got the PDF for this, so we can look at it together. Let's see. So this is the book I'm using for this, where I got this idea from. These ideas were in here. So it's chapter 1. Can you see my screen? Yeah. Okay. So it's
Yes.
good. Okay, so this is it. Yeah, so let me pull up my my notes. So what I'm saying is that the integral of directions of phi times k is 0, and it's the same as Frank Shu says here. Okay. Moreover, for many applications, we may make a further simplification and assume that this is 0. Since electrons, atoms, molecules, and even grains scatter equally in the forward and backward directions. This is not always true. That's the problem I was having. That's interesting. This is not 0. Just couldn't prove it. We're assuming it's 0 when there is a forward-backward scattering symmetry. Okay. So it's what you say, Felipe. This is indeed 0 when this phase function is symmetric.
So for forward backward symmetries means that in the case that we are using k prime, so the probability function is going to be the same as in the direction of k prime and contrary to k prime. So in that case, okay.
I'm trying to draw this. I'll try to explain this by
I'm
drawing
trying to
it.
draw it too.
Okay. Yeah.
I don't know how.
Yeah. Okay. So we have a grain, something. Okay. And we're looking at scattering. This would be the direction k. Okay. And this is photons coming from direction k prime. So we have a photon hits here, the target, and it's scattered in the k direction. Okay. So phi k prime k would be the probability distribution associated to this reflection. Okay. This is vectorial. So what forward backward scattering symmetry means is, let's say, how could we actually, maybe I should fix, for instance, so let's fix the direction K. So this is the incident direction K prime. We're going to write it as unit vector. So we'll set, let's see if we can change theta or phi. Let's put well, this is coordinated.
So
theta.
maybe not that. So forward backward symmetry means that that, for example, phi k prime that k is equal to phi minus k prime with the minus inside, minus k prime that k, which means it's a even function or an uneven function. So that you are
Philippe, wait. So you're saying, I'm not sure this is this. Yeah, and you're saying that the forward backward scattering means this. So it's the symmetry.
So it's the same probability. So if I'm coming from one direction, and there is a chance for me to go to the direction k, then it is the same direction. It is the same chance as if I'm going backward in the same direction to move to the direction k. Is that what forward backward symmetry?
That's correct. I think that's correct. So going back to my drawing, we have, this would be forward scattering. So if I say this is the same probability as the backward scattering, that would be coming from this direction. And then
No. From direction minus k prime.
That's correct. From forward would be this one.
So yeah, I think that would be phi k k dash comma k equal to phi minus k dash comma minus k. Don't you think?
What do you mean by that? Prime.
That could be because, but that's because of the for the symmetry in phi. So you can exchange one to the other. So k prime and k not prime. But what you're saying then is
I think that you're right. This means forward. I agree. This is forward backward scattering asymmetry. So it means that this is an even function. Okay. And since we're integrating a knot, so this is the integral of d omega k times 5. So we'll put it in the primes since. So this is even in k, and this is odd. So I think that it looks good in terms of this being 0. But I think what I wanted to do earlier was just to put phi prime to 0. So this way we have, I can make a sketch. So if I say that phi prime is 0, we are so in this case, well, no, it doesn't work either because I need to. I wanted to draw the phase function. So that would be theta, phi of theta. So how would that look like? Then it goes from 0 to pi only.
Constant.
Say?
It should be constant irrespective of theta, since we are assuming isotropic.
I misheard, Pratyush, sorry.
I think this phi of theta should be constant irrespective of theta because we're assuming isotropic scattering.
No, it's not isotropic. That's the point. It's not isotropic. It's symmetric, forward backward symmetry, but it's not isotropic. Okay, so I think we're having this situation now, where this is symmetric between the two. Something like that. And I'm not sure if this helps, but it's symmetric relative to the middle here. So pi, half pi. But let's go back here. Can we claim that this is obviously zero? So okay, well, let's I think we can. I think this is a very simple argument. We're saying that the omega k times phi k prime. Okay, this is a vector. That's the integral we want to show. And so we have that if we change k into minus k, that's going to be the same as the integral of the omega k phi minus k. And so this is minus the integral of the omega of minus k. Okay. Let me see, I've put a minus here, but this is not the right one. I also need to put another minus here. So this would be minus and plus. So the integral, no, it doesn't work like that. Sorry. Guys, I'm sorry, I'm getting confused here. Let me give it one last go. This is plus, I'll put the minus here. So we're saying this is forward backward scattering symmetry. I can place the plus and minus here in k prime, okay? So that would be the integral of k prime, okay? So we're saying that the integral is the same as, that's what we're saying, basically. Is that enough to conclude that it's zero? I'm not sure. I know that this is symmetric.
I found a sketch of the forward backward symmetry phase function.
Okay. Can you share? Do you want to show us?
Yes, please.
Go ahead.
Okay, so here it shows the forward scattering and the backward scattering.
Yeah.
So I think that if there is a forward backward symmetry, then this should be a lobe equally here and a lobe there.
Yes, we agree. Yeah.
So we have the light coming from here to there. So this is for each of the direction k. We have an integral of the of these directions projected to the direction of the light coming. So this should be k prime.
Yeah.
So this is k
Yes.
in that direction, and all of these are k primes. And
Yeah.
we're integrated over all k primes. And if this lobe is equally large as that is the same lobe here as there, then the contribution from this part would be canceled out by the contribution of this, of the other part. You see it?
Oh, I think yeah. You want me to
So we
sketch
were
this
going
or then-
to project this. There's going to be a contribution from this, from the chance from going here to there. There's a contribution,
Mhm.
but it's the same contribution and contrary to the chance of going here to there.
Yeah. I agree.
So it's the same going backward and forward.
But it'd be nice if we could prove it, right? I mean, in terms of write it down.
Yeah, yeah, I
Can
think.
you write it down, Felipe? Or maybe I think I can. I think we should be able to do this. Let me share screen again. I think we're almost there. So I think it's something like that. But we but you want to put k to, because we could integrate over the primes and fix the direction k if it's easier to think about. So we could fix k along z, for instance. That might be easier to think of. But let me, I mean, maybe this is trivial and we're just not seeing it, because I think that you're right in saying that this is symmetry that the when the drawing you just showed us, Felipe, is this one. So it's we have like a straight line. Okay, this is k, and we'll put it along z. Okay, and what you said is this: is that we have a two-lobe structure for the phase function, which is drawn here, and it's the same in the two lobes. Okay, so if I draw, so that would be phi of z in the direction k prime. And so if I had to draw the phase function for phi as a function of theta prime, I would have something like this, right? So this is a maximum in the direction of theta prime 0, then it goes to 0, and then it goes up again. We agree on this, yeah?
Yes, but I think that the difference is, well, the chance, the phi is a chance probability, so it's always positive. There's no way of summing positive numbers and getting 0. So I think what happens is that this plot here is not the phase, it's not this, but is the integrated light of the, so there's light coming, and that is the direction of the light going out. So you can so there's a part of the light that is going in direction k prime, and some part of the light that is going to k minus prime, to minus k prime. So that's how you can sum two.
Yeah. I think
So you have a positive
I think that's
thing
the
and a
phenomenon.
negative, and you can get 0.
I think you're right. I just want to put it down in equations. I think this is the correct explanation. But maybe we should follow this setup you proposed, Felipe. So we write down the integral of in the primes, okay? K primes times phi, k primes times k, and we are integrating over to the omega primes. And this one here, we fixed to z without loss of generality, because we can always change the system of reference later. So, and that's a vector equation. So let's look at the z component. Okay, so I'll focus now on the z component here. Okay, so that's going to be k prime z. It's going to be the integral of cos theta times phi of theta prime phi prime times z. So this is going to be theta equals 0 and phi whatever. But it's along the z direction. So d omega prime times sine theta prime d theta prime d phi prime. And this one here is d cos theta with a minus. Yes. So this closed integral would be then the integral over. So the phi part we will assume is symmetric in the direction phi is going to 2 pi is going to come out. No, yeah, because this doesn't depend on phi, the kz. So we have the integral of when theta is 0, this is going to be cos theta 1 to minus 1 times d cos theta with a minus here times cos theta times phi, which depends on cos theta prime. And so we have, and this is, hold on, this is cos theta prime, and this is also a prime here. So we have primes in here as well. So this is going to be 2 pi times the integral from -1 to 1 of d mu prime times phi of mu prime. Okay, I got it, I think. So this is the integral. So we are integrating. This function is the same as phi of minus mu prime, and this is even, and this is odd. So this is indeed 0. Felipe, did you follow? I think you're busy working out. you were computing on your side, I think. But this is the proof.
Yes, I was listening.
Okay, but I think we solved it because at least in the z component it works. Okay, I think that if I like following this sketch, so your setup here, I'm putting k in the direction z. Okay, so I'm projecting this integral we're trying to prove is 0 over the z-axis, and so k prime is cos theta prime, and the phase function is only going to depend on theta and phi prime because of fixed k to direction z. Okay, and so this k prime, I've changed variables to the cos, so the mu variable, and then I end up with this. So this is
an even integration, yes.
Yeah, but I think that okay, but I think that we should be able to prove the same from here. It should be straightforward to show the same from at this stage, because this is odd and this is even with the same argument, without going through the components or anything.
Yes, I think that we can say that phi is even because of the sketch.
Because of the sketch, what you said, I mean, this is a forward-backward scattering symmetry means that these two are equal when I change the sign here, okay? But the phase function is also symmetric in the sense that I can change, this is the same as So this is I of k, and I change to minus k prime. Yeah. K prime. You should be able to conclude from here that it's 0. And if I change k to, yeah. Well, sorry guys. I mean, I think we've not made much progress. It's already 1 hour into the lecture. I think we have to stop at some point. I think this should be pretty obvious why this is 0 if this is if this is even. So maybe on Thursday you can show me the proof in this vectorial form without having to go through the components. But I think for now we need to stop. At least we found that this is not always 0, and so that's it's indeed very difficult to prove in the general case. It's only true when we have forward-backward scattering symmetry. Okay. So that's something I learned today. So thanks for that, and we'll continue. We'll start from here, right? We'll try to prove from here to Thursday. So we have for first homework is show that this is 0 using these equations here. So on Thursday we'll catch up. Okay, Pratyush?
Yes. Okay.
Okay, Felipe. Gracias por la ayuda. Chao.
Welcome. De nada.